Yeah, so it's great to be back in Grenoble. I did my postdoc with Jean-Pierre, and it was a great time. So it's always great to be back. Right, so here's the outline of the talk. So I thought I would give a survey of the probabilistic construction of canonical metrics that I've been playing with for a couple of years now. So I would start with the case where X is a variety of positive Kodaira dimension, where it turns out that everything can really be worked out and it works really smoothly and everything. Then I will move on to the case when X is a Fano variety, where the picture is largely conjectural. So hopefully you will be as excited about this as I am, and you'll be able to solve all the open problems. That would be great. So then I will sort of, if that is the case, I will have succeeded with the goal of my talk, I think, if you can prove these things. Then I will talk about the case when X is toric, where it turns out that this conjectural picture can be validated if one looks as a sort of a deformation of the problem in terms of tropicalization, which simplifies things and where everything then works out well. Okay, so here's the motivation. So let's start with the sort of simplest case where X is an n-dimensional complex projective algebraic variety. And I consider the case where the canonical bundle is positive. So we have, yeah. Oh, I have to, can't hear me? Speak up. Okay, speak up. Okay, I'll try to do my best. Okay, so then by the Aubin-Yau theorem, we know that X admits a Kähler-Einstien metric of negative curvature. So if I have a canonical metric, it means that I have a canonical volume form. And conversely, as you know, we can recover the metric from the volume form. That's sort of the magic of complex Kähler geometry, right? So somehow, you can think of the fundamental object as being a volume form. So let's do it today because that's useful for my purposes. So we have a canonical volume form. That's the thing. And then when we consider varieties of positive Kodaira dimension, Song-Tian and Tsuji have constructed a canonical metric or singular metric on these varieties in general. So positive Kodaira dimension just somehow means that there is enough intelligent life on X, right? So there are many sections of high powers of the canonical line bundle. That's the definition of positive Kodaira dimension. And as once you have a canonical, it means you have a canonical measure. It's not an honest volume form now because the variety is complicated, but it's canonical measure. And let's say we normalize it, so it's a canonical probability measure, and it's birationally invariant, so it's a very natural object to look at. Okay, so what about this probabilistic point of view that I've been playing with? So I think it's sort of summarized in this picture of a flock of birds I'd like you to keep in mind. So the question is, I mean, is there a canonical way of sampling n points on the variety X at random? So this canonical measure somehow emerges in the large n limit. Just the same thing as the points of the birds in this flock, and what you see emerge is the shape of the whole flock somehow. That's the Kähler-Einstien metric, if you will. Okay, so there is a way to do this, obviously. So we could always sample with respect to the canonical measure. Then, guess what we recover? Well, the canonical measure. So we can all go home. I mean, there's nothing to talk about. But then, I mean, that's cheating, right? Because we really want to recover the measure from this process. We cannot put it in from the very beginning. So more specifically, what I'd like to do is this sampling procedure should really be encoded by the algebraic structure of the variety. So it should be encoded in the canonical ring of the variety. So it should somehow, it should be specified in terms of this algebraic data. And then in this large n limit, we really like to recover this differential geometric or, well, analytic object, which is the canonical measure or metric. So this really is in accordance with the usual philosophy in Kähler geometry, which I guess goes back to Yau, where we look at high powers of line bundles. So that's what I'd like to do. Okay, so let me give you the definition of this canonical probability measure then that you can construct. Okay, so I will call capital NK the dimension of the space of these sections. So by definition, nk tends to infinity. That's because the variety has positive Kodaira dimension. And the goal then is to define a sequence of probability measures on the n-fold products of x, which are symmetric. So that means that they are invariant under the permutation group. Because if we can do that, what it means is that the probability measure descends to the space of configuration of endpoints. What that means by definition is that we have a random point process with n particles. So we can sample particles by definition. OK, so how can we build such a probability measure in a canonical way? OK, so to define a probability measure on this product, what we need to do is just to pick a canonical element in this space of sections over the n-fold product. So it's like a holomorphic top form, or the kth root of this object is sort of a holomorphic top form. Because if we have that, then we can just form, everything will transform in the right way so that this object here, when I take a kth root in the usual way, is really transforming as an honest measure. I can write it down in local coordinates, but it will globally transform in the right way to have a measure. I just put in a normalizing constant to get an honest probability measure. OK, so we're in sort of looking for this fantastic section which will be canonical and work for us. So what do we really want? Well, as I said, we want this object to be symmetric when I take an absolute value, because we want a symmetric probability measure. And also, there is this liberty that it's enough if this section is defined up to a multiplicative constant, because anyway, I'm normalizing. So the constant will go away. OK, so we have these two demands. And it turns out that there is a very natural way to do this. So what you do is that you look in this space. You want to find this particular section, particular element. And you think of this as a tensor product coming from X. And inside this tensor product, we can just take the section to be a generator of the determinant line. So that's the totally antisymmetric part in that space. And by linear algebra, it's one-dimensional. So that's what I'm going to take. And very concretely, if you want to have a formula for it, you just take a base is in this space. And then you get this totally antisymmetric object in the usual way by a determinant. That's, I guess, one of the definitions of a determinant. OK, so it's a sort of locally holomorphic function on the n-fold product. But it transforms in such a way it gives me an honest measure. And I will, well, sometimes I call this a generator det, but I think I've removed it from the notation in this talk. So it's just SK is this canonical section. And it's enough canonical for this to give a probability measure, as I said, which is canonical. And then because the measure is canonical, it doesn't depend on any other thing than the complex structure, et cetera. You can see that it's really birationally invariant if you interpret it in the right way. OK, so great. So we have a way of sampling endpoints in a completely canonical way. And the question is, if we do this, do we see anything emerging from? That would be a canonical sort of emergent object, like this bird flock. OK, here's the bird flock again. It's the only picture. So OK, so the theorem is that if is a projective variety with positive Kodaira dimension, then indeed the empirical measures of the canonical random point press. So what's that? Well, it means that every time I pick n points, that will give me a discrete measure with Dirac masses at those points. So this is now a random measure. And I can ask, does it converge in probability or in law in any reasonable sense to something which is a deterministic object? So that's, just some basic, standard probability theory to make sense of that. But let's just think about it intuitively if you don't have that background. And the theorem says that, indeed, it converges in law towards this canonical measure. So you really see it emerging. What this means is that if you simulate this on a computer and you sample points in a region, what it means is that the number of points in that region, the proportional number of points in that region, will be the mass of the canonical measure in this region. This is actually it's stronger than that statement, but that's what it means. Okay, so concretely what it means if you're not interested in probability, so then what that means is, for example, when the canonical bundle is positive, it implies that you have a sequence of canonical volume forms on X that you get by pushing forward this measure on the n-fold product by integrating away all but one variable. And this you can see that this is a volume sequence of volume forms, and they really converge to the volume form of the Kähler-Einstien matrix. And this is a fairly explicit object. Okay, and another corollary is that you can really recover the metric, as I said before, in that by this formula. You can see that so this is a sequence of canonical Kähler metrics that you get from this object, which is this section, by integrating away again and taking d bar. It turns out that this is really an honest Kähler form, and it converges weakly towards the unique Kähler-Einstien metric on X. And then more generally, it even works. I mean, that's one of the good news of this probabilistic approach. Somehow, when it works in the sort of simplest setting, then it works in the singular setting as well, because it's sort of robust. I mean, so it really also works in the case of a variety of general type. Then these currents are Kähler currents, which are singular on the augmented base locus, or the base locus, rather. But they really converge to this canonical singular Kähler-Einstien metric, which was first constructed, I believe, by Esigiu, Gibbs, and Zeriai. And then there's been a lot of work, as you know, on these things. Somehow, I think it's interesting to think of these as sort of analogs of balanced metrics that were introduced by Donaldson, especially in the sort of setting of the canonical line bundle. There's a special notion of balanced metric. So I think this is somehow similar to the convergence of those balanced metric, but it would be interesting to make a more concrete relation. I don't know how to do that, but that would be interesting. Okay, so as I said, one virtue is that it really works in the singular and degenerate settings as well. Right, so the proof of the theorem really shows something which is much stronger. And it shows that the convergence is really, towards this deterministic limit, is really exponential in the sense of large deviations. So what that really means is that you really, I mean, it's like you have a picture of like when you approximate the Dirac mass by some like bump functions, then you can ask, I mean, what does the profile looks like? And the large deviation result really tells you what is the rate function of this profile. And it turns out that it's defined on the space of measures, but if you transfer it to the space of Kähler metrics, it's really just the Mabuchi's K energy. So somehow, surprisingly, the K energy shows up here as a rate functional. So I will say something about this large deviation proof, but the funny thing somehow is that I don't know how to prove this without proving this stronger version. I mean, really, if you were interested in the weakest corollary of the result, I still need to prove this large deviation result. It's the only way I can prove things. Okay, so let's move on to the much more challenging Fano case. So now we're in the opposite setting, where X is a Fano manifold, so the anti-canonical bundle is positive. And then, I mean, a Kähler-Einstien metric, if it exists, must have positive Ricci curvature. And by the famous Yau-Tian-Donaldson conjecture, I mean, X does admit the Kähler-Einstien metric only if and only if it's K polystable, sometimes called K stable. So there are stability type obstructions, and they are the only ones that exist. So this has finally then been settled by Chen, Donaldson, and Sun. For the case when X is smooth, I believe it's still open for a general singular Fano variety. Alternative variational approach that we had together with Sebastian Buxon and Mathias Jonsson, which shows a different version of the version of the result. So a Fano manifold admits a unique Kähler-Einstien metric if and only if it's uniformly K stable. So it's a stronger notion of K stability. here we have unique, but I mean, you can also, well, there's a sort of a poly version of this as well. But that's a different variation approach, which somehow turns out seems to be more related to the probabilistic approach, even if it's not entirely clear how they fit together, I should say. Okay, so what about the probabilistic approach in the Fano case? Okay, so why change some a recipe which had some success? Let's try everything again. So what did we do before? Well, we wrote down this canonical probability measure, which was built from these vector spaces. Here's a typo. If you put back the plus here, then we cannot work with the space because it's trivial, because it's the anti-canonical bundle which is positive. I mean, there is no intelligent life variety, only anti-intelligent life, I guess, whatever that means. Alien life or whatever. Artificial intelligence, maybe. So we need to work with these spaces, obviously. Okay, what's the problem? Just put back the section built from this space, and let's do what we did before. Well, if you want to get that honest measure, for things to transform in the right way, you need to put the minus sign here, right? Okay, let's put the minus sign. Let's not be scared. Okay. But then there is a problem. The problem is that there is no reason that the normalizing constant should be finite now, right? Because we're integrating 1 over a function which vanishes on a subvariety, on a hypersurface, and it could may very well diverge. Well, that's actually good news, I guess, because we need abstractions. Otherwise, things are working too smoothly because we know there is an abstraction, which is K-stability. So then what I propose is to define a new notion of stability, which I call Gibbs stability. I think maybe this will be clear later why the name of Gibbs could be attached to this. If this normalizing constant is finite, if what to do if we can proceed with this approach, basically. Okay, that's Gibbs stability. So then the natural conjecture then would be that a Fano manifold is Gibbs stable if and only it admits a unique Kähler-Einstien metric. So unique here comes, I will come back to that, but because we're talking about Gibbs stability, not Gibbs poly stability for the moment. Okay. Well, and then the conjecture is that if this is the case, then we can recover the Kähler-Einstien metric in this limit of many points as before. So that's the conjecture that I hope you will be able to solve. Okay, so let's say something more about Gibbs stability because there has been some progress on this. So even though I wrote down this condition in terms of an analytic definition, which is the finiteness of an integral, it turns out that it admits a very natural algebro-geometric interpretation, which is in some sense standards because it goes back, I mean, it's about the connection between integrability exponents and log canonical thresholds that I will come back to. So, okay, so to explain this algebraic notion, let's look at the hypersurface that it's cut out by this canonical section. It's really a very natural hypersurface or singular or a divisor in the n-fold product, which is a sort of an incident divisor, right? So when is a configuration of points on this hypersurface? Well, it's exactly when it's sort of in a bad position in the sense that we can find some section in the space passing through all these points. That's a rare condition, and it cuts out the hypersurface in the space of configuration of points. So if we then normalize this divisor by k, we get the q divisor on the product, which is it's linearly equivalent to the anti-canonical divisor on the product by definition. So then Gibbs stability of a Fano variety at level k means that this divisor has mild singularities in the sense of the minimal model program. So it has Kawamata log terminal singularities. So this is because the integrability condition can be formulated as some log canonical threshold being strictly bigger than 1. So that's sort of immediate from the definition. So, and I think, for example, actually, Jean-Pierre together with Kähler have written an important paper on these relations. So I mean, this is just a reformulation using that language in terms of, so we get this condition in terms of log canonical thresholds. But then once you have this condition, you can see what the sort of stronger uniform version of Gibbs stability should be. Well, it should just demand that the lim-inf over k is really strictly bigger than 1. I mean, in this case, there is a risk that this tends to 1, right? So let's say that it's uniformly Gibbs stable if that's the case. And I think this is a more useful notion, actually. And then it turns out that using MMP techniques, so Kento Fujita and Kento Fujita together with Yuji Udaka, so Kento is there, yeah. They managed to prove some really great results. So they proved that uniform Gibbs stability indeed implies uniform K stability, which is consistent with the conjecture item. This is a purely algebraic proof and argument. So given the resolution of the Yau-Tian-Donaldson conjecture, indeed uniform Gibbs stability implies the existence of a Kähler-Einstien metric. But this does not use the probabilistic approach. So then what's open is, for example, the convergence of the point processes in this case, and also the converse implication, which seems very challenging, right? Intriguing, I'd say. Even on P2, it's open, I should say. So I don't know if P2 is Gibbs. Well, it cannot be Gibbs stable because it should be sort of Gibbs polystable, but I don't know if it's Gibbs sim stable, for example. Never mind. But it's true on P1, so don't worry. Okay. So let's say something about the case when the automorphism group, the connected component is non-trivial. So this is the case, if this is the case where there's a difference between K polystability and K stability. So, okay. So if it's non-trivial, then X will never be Gibbs stable. You can see that. So this integral will always diverge. And that's as it should be, because the variety is not K-stable. It's only K polystable. And you can actually, so just give me a simple reason for why this is the case. You can prove this by sort of a contradiction, because if it was finite, you could normalize. You will get this probability measure on the space of n points. And then you could push that forward to get a very canonical object on X, which is a measure. It's like a ridiculously canonical object because it's invariant under the whole automorphism group. But no such things exist. It cannot be invariant under both the sort of a compact subgroup and its complexification. So that's how you could prove this, for example. So what we need to do is to break the symmetry, this huge symmetry. We need to break it. So we break it by fixing some background volume form. So it induces a metric on the anti-canonical line bundle. And then what I'm going to do is that I'm going to sort of do a regularization. So for some sufficiently small positive number gamma, I look at these regularized probability measures. If gamma is really, really small, then you can see, it's not hard to see that this will really converge. It will be a finite, well-defined object. Okay, so mind you, I use the volume form here because I need to split. I need to have something to integrate with here, and I need absolute value here. Otherwise, this is not well defined when gamma is different from 1. It's just when gamma is 1, it turns out that these two objects cancel. So that's why it's canonical. Now it's not canonical anymore. And you can see what the sort of critical exponent here is. By definition, it's the lim-inf of these log canonical thresholds. So it could be that it's smaller than 1, like 1/2, and then you work with gamma up to 1/2. Then you have an honest probability measure. So let's call gamma the sort of critical exponent. And here's the conjecture then in this situation. The conjecture is that the critical exponent here, gamma, coincides with the sup over all gamma such that Aubin's equation admits a solution. So this is a bit more complicated. I mean, actually, gamma could be bigger than 1. Because, I mean, I didn't put any restrictions on gamma. And then in that case, there could be many sort of unstable solutions. So then in that case, what the conjecture says is that the existence of a minimizing solution in the sense that it minimizes the K energy. But I mean, we're really mainly interested in the case where gamma is at most 1. So then the conjecture is that if gamma is smaller than or equal, or if gamma is in this range, then the probability measure is well defined up to this critical gamma. We could sample, and the conjecture is really then that what emerges in the large N limit is the solution to Aubin's equation for this given gamma. And then if you assume that X is Gibbs polystable, whatever that means, then the conjecture is that you really get the Kähler-Einstien metric by first letting N tend to infinity with gamma strictly smaller than 1, so you can get started. And then you let gamma tend to 1. So this is like this famous picture of symmetry breaking in the physics literature. It's like the space of solutions in the sort of ground state that we're looking at. It has some symmetry. It's not unique. So in order to pick up a particular solution, we need to break that symmetry. So we need to start something here and then go down, and then we pick up something. That's the picture. And I haven't defined Gibbs polystable here because that's actually a bit work in progress. It's not. That's actually quite intriguing how you should define Gibbs polystable. But whatever that notion is, it should give this result. Okay, so what's the relation to statistical mechanics? Because there is such a relation, and that is really part of the proof strategy. Okay, so as I said, we can always fix a background volume form. And then let's just, in a very general situation, let's fix some real number beta, and let's look at this probability measure here, if it's well defined. So the point is that in the case of a variety of, say, general type, then we should take beta equal to 1, and then this turns out to be independent of the background metric, volume form. And in the case of a Fano, we should take beta equal to -1. And then this is, again, canonical. But it's useful to work in this general situation because then you can deform beta. OK, so then there is this tautological way of rewriting this probability measure in the following way. So I just define E to be what you need it to be for this to make sense here. So why do I do this? Because then now it really fits into the setting of statistical mechanics. Because then I can, so in general, a probability measure of this form is the Gibbs measure or the Boltzmann-Gibbs measure, which describes the equilibrium distribution of n particles on X interacting by this energy function En at inverse temperature beta. So here's the, I mean, I think Valentino asked for the meaning of it. It's the same beta, and this is why it appears as an inverse temperature. So in our case, this interaction is really a sort of like a virtual energy. I mean, not for the moment, it has no physical meaning. It's just some sort of virtual physical theory, but it's useful to think of it as an energy if we want this analogy to be here. OK, and then there is one funny thing, as I said, when we take beta negative, that sounds funny. It's negative temperature, which I guess is not that strange to a Swede. I'm pretty used to negative, but here we're really, in this picture, we're talking absolute temperatures, Kelvin, so you should not be able to go below 0. Even in Sweden, you cannot go below 0 temperature, I hope. But in that case, this is just formal. You can just switch the sign, obviously, of the energy, and then, I mean, it's positive, the temperature is positive. So here it turns out that if you take the sort of conventional sign here, where beta is positive, and the energy is repulsive. So because of this, the density is the determinant. It vanishes when 2 points merge. So it means that it's very rare that 2 points really come close in a probabilistic sense. So it means that the energy is pulling them apart. It's repulsive. And when we switch the sign, it's an attractive energy. And then you see why it should be more unstable, because all the points, if there was no thermal motion, all the points would just collapse into a singular state. But then there is this thermal motion from the temperature, which is sort of making things more fuzzy. So here's the picture that at low temperature, they tend to go down to the minima of E, but when you, at negative temperature, they really go down to up to the tops. Okay, so the starting point of the proof then, I mean, why is this useful? For the moment, I've just reformulated things. But then the reason it's useful is that it's this E energy thing which has a natural limit when n tends to really the starting point of the connection between finite number of particles and n equal to infinity. Because based on some previous work with Sébastien Buxon, that we were working on for completely different reasons, I guess, you can prove that this object in some sense converges to something just depending on the limiting measure here. So if I have a cloud of points, which when you look at it from very far away really looks like some smooth, nice, continuous distribution of a measure mu, then for many points this object can be approximated with this. Now, this is in the sense of what is called gamma convergence, in the sense of de Giorgi, but that's more or less like saying that there is a weak type convergence. I'm not going into what, but it turns out to be a very useful notion of convergence. This limiting object is really what is called the pluricomplex energy in the literature. So I guess we first introduced this notion in my work with Sébastien Buxon, Vincent Guedj, and Ahmed Zayei. But you can, when mu is smooth, you can write it in terms of the potential as just the I minus j function in Kähler geometry. So I'm saying that this object really emerges from this object here. Okay, so once you have this connection, it suggests what should happen here. Because what are we doing? You're asking, what is the probability of finding a cloud of points in some small ball in the space of measures around a given fixed measure mu? So that's what this is formalizing. What's the probability of when I sample points, I see the distribution looking like mu? What's the probability of seeing this phenomenon, this event? Well, it means by definition that you should integrate over this ball. But as I said, on that ball, when this configuration of points looks like mu, I just replace e to the mu, e of mu here. Take it out of the integral, and then I just integrate over that ball. Well, that has a rate functional, which is almost by definition the entropy. That was more or less proved by Boltzmann. And it almost appears on his thumb, I think, this relation. So what you see is that the rate functional that you get out here is energy plus entropy minus a normalizing constant. So this is classical when there is no energy. And what this shows is that the probability of seeing mu when you have many points is exponentially small unless it happens that f of mu is zero. F is zero on mu. So it should be a minimizer of this function. And then it turns out that you can see by doing some explicit calculation that this is really just the K energy in disguise. I mean, if you write the measure mu as a volume form of a Kähler metric, what you see is Mabuchi's K energy here. So somehow this explains the Chen-Tian formula for the K energy. It's an energy plus entropy contribution. I think it gives some sort of microscopic explanation of that. But this was just formal proof because, what did I do? I sort of replaced two limits of small ball, many particles. If you really want to do this, you'd have to do some geometric analysis. And it turns out that it really works if you work using the uniform quasi-superharmonicity of the energy and some comparison results like the Chen-Yau gradient estimate and so forth, working on this orbifold. But it turns out that it works. But then if you want to handle the case where beta is negative, then this function is not superharmonic, where it's like the opposite. And then I think, what I believe is that you should really exploit that it's a pluri-subharmonic function. That's really what should be helping us. But it's far away still. But I think this is a hint if you want to start working on this. Use this. That's my hint. Okay, so just some supporting evidence for this conjecture. So it's not completely crazy. For the first, it actually holds when x is one-dimensional. Well, one-dimensional Fano, that's a little bit too boring. It's just P1. But you can look at log Fanos. All of this works in the setting when we work with a log pair of a variety and a divisor. So there's just a bunch of points on x. And then, like this American football, we have two singular points. And then Gibbs stability turns out to really be equivalent to uniform Gibbs stability and to K-stability for this log Fano variety. So that's comforting. And then I have a very, very weak confirmation of the general case that you can check that if x admits a Kähler-Einstien metric, then this rate functional, which gets identified with the K energy, is really lower semi-continuous on the space of probability measures. That's like if there is a large deviation principle, that by general always implies that the rate function is lower semi-continuous. So this would be conversely some very weak compatibility. And this is quite non-trivial, so it uses some compactness results that we proved with Sébastien Bouxon, Gibbs, Essedieu, and Zerier. So this is some sort of weak confirmation. Okay, so let me finally say something about the toric case, where everything becomes much more concrete. So I have how many minutes? 55, wow, okay, then I can do this. I think maybe we can even prove a new result. So now I'm looking at the case where x is a toric Fano variety. So it's just an equivariant compactification of a complex torus, C star n. And then by the usual toric dictionary, I can associate to x just a special type of polytope, which I have drawn here. And I let convex polytope, I take some enumeration of the lattice points here in Kp. And then we know that the corresponding multinomials I get here, so this is multinomial notation, they span the space of global sections. So we have a very concrete description of that space. So it means that we can write down what this measure should look like. So before I normalize, it looks like this. So the integrand here is the classical van der Monde determinant. So what it is just because you can see by writing out the determinant that you get sort of all kinds of sums of permutations of these multinomials. Extremely concrete, well, at least quite concrete. Then let's try to exploit the torus symmetry here. Okay, so because we have automorphisms, we know that any Kähler-Einstien metric actually respects the torus symmetry up to automorphism. So there is if there is a Kähler-Einstien metric, there is one which is invariant under the real torus. Okay, so in particular, its volume form really in some sense descends to Rn. All the information about this volume form is encoded in Rn, right? Because I can sort of just factor out so let's let x be the logarithmic coordinate living in Rn, and I sort of factor out the volume form along the torus fibers. Then I can identify this volume form with where a priori psi of z is a plurisubharmonic function. The weight now becomes a convex function on Rn. So it means that in this classical dictionary, plurisubharmonic and torus invariant here just corresponds to convex, as you know, in Rn. So that's very good. Okay, so let's try to do this with our measure to see if things simplify. Well, unfortunately, that doesn't work, right? I mean, this object is not invariant under the real torus that we had here. I mean, it's the log of the polynomial, absolute value of a polynomial. It does not respect the torus symmetry. Okay, is that bad news? I don't know. Well, this is where tropicalization comes to our rescue. So it means that instead of living in Sweden, you now live in Brazil or something, where the weather is much nicer. And then you relax and you come up with some new ideas. So what is the philosophy of tropicalization? That's to replace an elusive problem about polynomials in C star n with a simpler one for piecewise affine convex functions in Rn. That's the philosophy of tropicalization. And the recipe is this. Every time you see a polynomial like this, you just replace it with this convex function here. That's more or less the procedure of tropicalization. So in analytic terms, what it says that every time you see a plurisubharmonic function, or some C star D, should be, then you just replace it by a convex function you get by deforming it in a sort of a large complex structure limit somehow, like this. Okay. Okay, so let's apply this philosophy. What can tropicalization do for us? It will not solve the original problem, but it will maybe solve a simpler problem. So if you apply this, it means that you replace this measure, complicated measure with the Vandermonde determinant on C star to some high power with this e to the minus what I call the tropical energy. The tropical energy is what you get by tropicalizing the determinant. And what it is actually what is in the literature called a tropical permanent. So it's a very concrete thing is just remember these are the lattice points in my fixed polytope, which is they are fixed once and for all. And then I get a function of the configuration of n points by just maximizing this sum. Here. This is what you get from this recipe. But then it turns out that this has a very natural interpretation in terms of optimal transport theory. Because what is this? If you take the minus here, it means that you're minimizing a function which basically looks like x minus m squared, absolute squared, up to some irrelevant terms. And what it tells you is, that, so what is its value on this configuration of points, which is changing? Well, it just, what it is the optimal cost, the minimal cost of transporting these points to these points. So what it means is that you start with the configuration of points. You look at this matching problem. How can I match all of these guys with guys here in a way to minimize this thing? And that's what the energy is telling you it should be. OK. So that's a concrete thing we could try to work with. And then you look at what is the role of the action of the automorphism group. Well, that's now the complexification of the real toric, just the translational action on Rn. And what you see is that this thing will never, because of the existence of this symmetry just as before, this thing will never be finite. I mean, you can see this because if you integrate and you split your variables and you integrate over the moment center of mass, this contribution will give infinity, you can see. So this will never converge. So tropicalization didn't help us. We cannot get started. But then, well, we have to do as before. We have to break the symmetry. So what I do is that I introduce some background volume form, which has a potential phi, depending on the polytope, and a gamma. And then I look at this new energy, where gamma plays a role. And gamma is strictly smaller than some integrability index. If you do this, then it turns out that you can really prove the analog of the conjecture I wrote down. So this is joint work with Magnus Onnheim, who graduated recently. So this critical exponent really coincides with the invariant which shows up in Aubin's continuity method, and which also coincides with the lower bound on the Ricci curvature of this toric variety. And when you're below this critical exponent, so that you can sample, then you really get the unique solution to the Aubin-Yau equation when n tends to infinity here. And also, if the variety is k polystable, then you really recover the Kähler-Einstien metric in this way by first letting n tend to infinity and then gamma tend to 1. And the proof, as I hinted, it really exploits the plurisubharmonicity, which now is the convexity of E. So it uses some sort of standard but highly non-trivial results about log concave probability measures coming from the, log concave means that E is convex, so that's the Prekoppa inequality and Borel's inequality, and then you can prove the thing. So I think I'll stop there. Thanks a lot for your attention.